Welcome to the next video lecture for Chapter 16. In this lecture, we will be covering sound and the properties of it. This will follow along in sections 16.5 and 16.6 in your textbook. Sound is a mechanical longitudinal wave. Mechanical meaning that it needs a medium to travel through, so it needs some particle, something to move through, and it is a longitudinal wave, meaning that the oscillation is in the same direction as the wave speed, as the wave itself. So that means the back and forth motion of the oscillation is in the same direction as the wave. When a sound wave is traveling, it's not that the air molecules themselves are actually moving towards you in one direction. They just oscillate back and forth. So they move to the right a little bit, and then they move back to the left. So what our eardrum detects is this difference in pressure. And this change in pressure is how we hear sound. So we'll talk about this a little bit more with the waves a little bit later on, and I'll show you a quick video in a second. But it's more that the molecules just move back and forth. A sound wave, or any longitudinal wave for that matter, creates areas of compression and rarefaction, or condensation and rarefaction. An area of, I really like the word compression better than condensation, but that's how we see it here in the lectures, and that's how we see it in the book sometimes. So an area of compression is where all the molecules are tightly forced together, and an area of rarefaction is where they're spread out. So it's a compression or condensation is that there's a very high density of air molecules or whatever molecules the medium's traveling through, and an area of rarefaction, it's a low density. The molecules are spread out. The distance, and we've already seen this is just kind of like a little bit more of a review here. The distance between two areas of compression is a wavelength. Or you could say it's the distance between two areas of rarefaction. And one full cycle contains both an area of compression and an area of rarefaction. And frequency is the number of cycles moving by in a given location, for any given location, number of cycles per second. So we've seen this all before: frequency, number of cycles per second; wavelength, the distance of one cycle, the length of one cycle. Really straightforward. Now we're just applying it to longitudinal waves. So when we talk about sound, and we generally refer to the different types of sound waves that we hear by their frequency. Now, humans have a hearing range that runs from about 20 to 20,000 hertz, so we can hear all ranges within that. Dogs and other animals can hear much higher sound frequencies. And most of the stuff that we hear on a daily basis, for example, you hearing my voice, has actually composed of multiple different frequencies together. A pure tone is just a sound of one consistent frequency. So if you think of like a touch tone phone, where if you hit the button, it makes a beep, and there's a different beep for each one, and as it goes through, each number corresponds to a different tone, and as they combine, you can get just one certain frequency. So here's kind of like a little chart here showing how a touch tone phone works. But infrasonic refers to sound waves that are below the frequency of the average human hearing, whereas ultrasonic refers to frequencies of sound that are above the average for human hearing. So below 20 hertz or above 20,000 hertz. Here's a couple of drawings and a couple graphs that make the comparison between pressure and the areas of rarefaction and compression. An area of rarefaction is a low pressure, whereas an area of compression is a high pressure. The molecules are all tightly pushed together. We hear loudness, how loud or how intense a sound. Loudness is different than intensity, but how loud a sound is depends on the pressure. And this is usually when we, instead of taking it as a longitudinal wave, we can draw it out as a transverse wave with areas of low pressure and high pressure. And the amplitude of the air pressure and the difference from the undisturbed pressure of the air, so this is the difference from the undisturbed pressure of the air, depends on how loud, depends on the area of compression or rarefaction. That amplitude depends on the loudness. we won't particularly look at this. You won't ever be like assessed on loudness, but we may look at something about how decibels work. It's on a logarithmic scale, and we'll look at how loudness is different for that. But we'll talk about that later. The speed of a sound.
So here's a little simulation to show us how sound interacts with the particles around it. I have a speaker and kind of a fake little mock-up of the air molecules that are all nice and neatly arranged, which is not going to be true. Down here I have a pressure graph, and I can turn on this here. We'll hear what the sound is when we're produced, but I'm going to turn that off pretty quickly because it's really annoying. So if I turn this on and we start getting, let's turn the sound on there. Very low frequency, low pitch sound. As it's going back here, we have it moving through. Now, I'm going to turn this off because that is annoying. We have our sound, and what I'm going to show here, I'm going to actually increase the frequency just a little bit up to here or so. So that was a low frequency sound. Now we're going to go a little bit higher. And we'll give it a second for the simulation to kind of adjust. But you can already start to see the different areas of compression and rarefaction. So here we have an area of compression traveling outward. We have the rarefaction right in here. So if we pause this, you can see here the increase in pressure corresponds to this area of compression right here. And we have that lower area of pressure is a decrease, there's that rarefaction right there. The other things that we can look at on this from this graph here is we can look at the wavelength, or for one sound wave, by using the different the distance between a crest and a crest, or a trough and a trough. So let's get it to a good point here. So now we have about 30 centimeters or so right here to about 80 maybe. So it's a little over 50 centimeters for the wavelength. And then we can go through and we can actually figure out in time how long it takes for one wave to travel by. So we can go here and we can say, get this here and ready. We'll start it right when the wave hits the end. We'll say it when it hits the middle part right here. So ready, set, we'll start that. And then we'll stop it when another one comes by. So ready, set, right now. So that's 1.4 seconds, milliseconds actually. So it's 0.0014 or 146 seconds. And our wavelength of, we'll say 0.52 centimeters. So the important thing to do here for this, for our for the frequency, in order to use because what we found right there was the period, we need to take the inverse of the period to determine the frequency, and then if we multiply that by the wavelength, we can get the wave speed to be equal to a little bit too high, I think, on my calculator here, but it says that it's moving at 1,317 meters per second. So I don't know exactly how true this is, but hopefully you can kind of see the different, the actual kind of real life thing of what's happening through this simulation.
Sound depends on the type of material that it's traveling through. The speed of sound is fastest in solids, slowest in gas. It's really because the molecules in the solid are very close together, and it's very easy for them to transfer that energy as they move back and forth throughout there. Temperature also has an effect on the speed of a sound wave. So if you have high temperature gases, there's going to be a different speed for the sound out there. The speed of sound at room temperature no matter what frequency is always going to be room temperature. This is about 20 degrees Celsius, 343 meters per second. All right, 3 quick review questions based on the video lecture that you just watched. First, what is the difference between infrasonic and ultrasonic sound waves? Second, how do sound waves travel? Think about the type of wave. And finally, how is air pressure related to sound wave propagation? So please answer these questions online. Thank you very much. Have a good night, and I will see you in class.